Hi, I'm Martin. This is the second of two videos on a quick guide to user studies, in which we're looking at setting up a basic user experiment to compare System A and System B on some known factor. Previous video we looked at study design, ethical approval, forms logging, and their procedure. This video we're going to look at the analysis and look at descriptive statistics, statistical tests, and further reading, which is really important because I can't possibly cover everything that's needed in a short video. Statistics is a big, complicated field. It's a degree and postgrad degrees. Basic descriptive statistics you're looking at are the average and the mean, the average and the distribution. So, previous video I introduced the text entry study I was doing. Okay, so here we have the results I got from that study. Let's see if I can zoom this out a touch. So this is just in Excel. Output from the log files processed and spewed into Excel. This is the user ID, which is the date stamp and time that they did the study. This column is the time the person took on average, what their average speed was. Sorry, their words per minute, their average speed during the test sessions. Okay, for the standard keyboard and for the tilting keyboard. So this is how you need to get your data sorted. This is a person, user ID. Okay, this is that person's speed for the one condition, and this is their speed for the other condition. Or in generally, this is their measurement for one condition, and this is the same measurement for the other condition. And you have one row like that for everybody in your study. Okay. Important thing is these are paired numbers. Okay, so this person got 27 on the standard keyboard and 28 on the tilting keyboard. Okay, this person got 36 on the standard, 28 on the tilting. Okay, so what's the mean? The mean is basically the average. So first thing you might want to look at is the average, which is mean is the most common measure we use. So I can work out that in Excel using average. And you just average across your data. Okay? And if I copy that to the right, it will fix the equations. I may as well copy my headings. Should probably introduce a we'll call it mean. We'll be technical here and call it the mean. The mean is calculated by, this is what we call an average in school, usually, or we remember as an average from school. So schools do call it mean. You sum up all these numbers and divide by the number of them. Okay, so it tells you the average score. Okay. Sometimes we don't want to use the mean though. Sometimes the median is actually a more appropriate measure. This is particularly true when data is skewed. So in the UK just now we have a very heavily skewed income scale. There are some people who earn incredible amounts of money. Top directors earn the average salary in the first 6 days of the year. So the mean salary would add up the salaries of everybody in the UK and divide by the UK population. Okay, so that tells you what the average salary is. Okay, but that's distorted by people earning millions and millions. Okay, so the median salary is actually, if you put all the people in the UK in a line, you pick the one in the middle, what does that person earn? Okay, so that's more like what the average person earns than what the average salary is. Okay, so it's subtly different. Sometimes you have to use median if you don't have a continuous, if you don't have a true scale, you should use median instead of mean. The book will go into that in more detail. You also need a measure of how spread the data is. The mean tells you one thing. So here we've got a mean, and my mean is actually saying we had a mean speed of 29 for the standard keyboard and 27 for the tilting keyboard. That doesn't look good for my tilting keyboard. People were faster with the standard one. That's not looking good. But is it actually different? Well, that's higher than that. So yeah, this is better than that. Well, not necessarily. If you look at this data, there's actually a lot of noise in here. This person was faster, this person was slower, this person was faster, this person was faster. person was faster, that person was faster. Lots of people were faster with that keyboard, but there's actually a lot of noise in here. And some people were close, some people were quite far. There are other people who were faster with the tilting keyboard. So can we actually make a safe conclusion that if we took this study and ran it with a much, much bigger population, we would actually get the same result? Or is this result just down to chance? And that's what statistics are trying to help you with. Is it down to chance? One of the things that come into this is a measure of the deviation. It's time to talk a wee bit about normals. This is a normal curve. So in the middle here we have the average, okay? And on what we've got is a histogram or a frequency chart. So if you measure something like reaction time, any human activity, even human height, so people's height in Scotland, there will be an average height and it tends to drift away the further away you get from the average, okay? So this is the bell curve or a normal distribution. This is like the perfect case where it fades away equally on both sides. Okay? A lot of human response activity actually follows normal distribution. So a lot of data is normally distributed, and if it is normally distributed, then you're approximating to one of these curves. Okay? These curves are all normally distributed, but they differ on their, and they've all got the same mean of 0, but they differ on their spread. Okay? In this one, there's actually very little variation, so most people are within half a point of the mean, okay, on this frequency chart. Whereas in the orange case, it's much more spread, so a lot of people are quite far away from the mean. So somehow you need a measure of the deviation, because that matters when you're comparing two systems, because if you had one graph like this and another one, if this blue graph, there was another system with a mean of 1 with the same blue graph, then that would be quite a distinct difference. But if you took the orange one and moved it up to 1, there'd hardly be any difference at all. So it's how much the two systems overlap helps you in deciding. Various things you can do here. You can calculate the standard deviation. There's actually 2 standard deviations. You're doing it for the sample, not for the whole population. Okay, and that's a slightly different calculation. But in Excel, you just do standard dev S, then give it the range. Scroll that down, and you see they've both got similar standard deviations, and it's about 5. That actually means that if you read Wikipedia on standard deviation or the book, you often see a graph like this, which shows that within one, that row symbol is standard deviation, within one standard deviation of the mean, you've actually got 68% of the population. So 34% occur within one less than it, 34% occur in one over it. So what this is actually telling you is that 68% of the data lies between roughly 24 and 33 words per minute. Okay. Books also talk about variance, which is closely related to standard deviation. You look that up. And sometimes you refer to the 95% confidence interval. And this is actually roughly where on this graph you would draw lines so that 95% of the data falls within those lines. It's not quite true. It's where you'd expect the result to occur if you ran the study 95 times. Or if you ran it 100 times, 95 times, you'll get a mean in here. Because that's one of the things that's really tricky about statistics is you've measured it with, I've measured it with like, how many people? 26 people here. If I was to do it with another 26, I'd get a different answer. And what the means are trying to tell you is, what the statistics is trying to tell you is what's the probability that if I repeated it with another group, I'd get the same answer. Okay, and you've got to have confidence, and that depends on the spread of the data and how stable the data is. If all these numbers were really close, then I'd be really confident. If they're completely all over the place, I think I ran it for another 26 people, I'm going to get a completely different answer. Okay, we'll come back to that in a minute. So how do we test if our data is normal? There's a test called the Shapiro-Wilk test. So if I take my data, so what a normality test does is it looks at a normal distribution of and tries to say what's the probability that the data we've got comes from a normal distribution. So if we went and surveyed the whole population, we get a nice bell curve. What's the probability that our data could come from that nice bell curve? So you take your data, you paste it in here, and you hit calculate, and it does the Shapiro-Wilk test, and its output is, so in this case we're trying to say that there is no difference. So we're actually trying to get we want our null hypothesis accepted here, because the null hypothesis is that our data follows the same distribution pattern we'd expect of a normal distribution. So our data seems normal because H0 has been accepted at the different p levels that I'll come back to later. Yeah, and we can do that for the other side. So our data seems normal. So it's safe to use. One of the reasons you have to do a normality test is to decide what statistical tests you can do. Some of them require your data to follow normal distributions, and they're actually usually the better test you can use if you can get away with it, but you have to test for normality first. So this measures the probability that your numbers come from a normal distribution. If the probability is less than or equal to 0.05, you have to say they're different. If it's greater, you can't say they're different, and in this case you can conclude that it's reasonable to proceed with a normal test. So, statistical tests. You'll usually have paired data, as I have. This is sometimes called a repeated study design, repeated measures design, sometimes called paired test. If your data is normally distributed, you can use a paired t-test. So different ways of doing paired t-tests. This online calculator is one way, and it's a really good way of doing it. It gives a little explanation of what's behind it. Then take you to the calculator. You paste in your two sets of data. Okay. Significance levels differ. So 0.05 is what we normally use in HCI studies. That means that we're willing to say this is a result if there's 5% or less chance of it being random. Okay, so we set a significant level at 5% or 0.05, and we're saying if this test say that the chance that this data is different, then we're willing to accept a 5% risk on it. In medicine, you're talking a 1% risk. If there's actual harm could be done by giving a drug or something, you want a bit more confidence. But 5% risk of us being wrong is reasonable in HCI. If you flick back to these are the tails of the curve. Okay, so these are the tails of the normal distribution. There's one tail there, and there's one tail there. Almost all statistical tests ask you whether you want to do one-tailed or two-tailed, and the answer is always two-tailed. Okay, you can do a one-tailed test if it is physically impossible. Say that system A is worse than system B. Okay, so is a car faster with a plain car or a car with a 10-ton weight on it? It's not going to be slower. It's not going to be faster with the 10-ton weight, but it might not make a difference. It's not the best example, but you've got to have a physical argument that it cannot be one way. Okay, not just a hunch. So we almost always do in fact, I've always done a two-tailed test. Okay, so you calculate that. It spits out the calculation because it shows you the different steps it's doing. It tells you the mean difference, okay, and then it does the t-test calculation. The t-test spits out a number, okay, which is the t result, and you look that number up in a table, or you use an online tool like this to convert that number into a probability. This is basically saying that the probability that they're the same is 0.015, okay, or 1.5% chance that they're the same, okay. Because that's less than our predetermined significance level of 0.05, we can say that is less than that, so we can claim there is a difference here. Okay, so there actually is a statistical difference here. The chances of the data being the same are so small, at only 1.5%, that we're willing to make the statement these are different. Which is bad news, because that means that actually my great tilting keyboard is slower than the standard keyboard. Sigh, science never works, sometimes doesn't work out as you want it. Okay. If your data is not normal, you can use a Wilcoxon signed pairs test. You run it much the same way, it gives the same answers, style, but because it can't assume normality, it's actually a weaker test because there's some calculations it has to do in a more vague way. So it's more likely to say we don't know, basically. One thing you've got to be really careful of in any statistical tests like this with users is pseudo-replication. This is like the #1 mistake people make in user studies, and I see lots of papers at conferences being rejected because they've pseudo-replicated, and it just invalidates your results. So how many people are in this picture? There are 4 people. If I get them to type in 10 phrases each in a user test, how many people are in the picture? There are 4 people. Yeah? There ain't 40. So your N in your study, the number that you're comparing is 4. It's not 40. The fact that they've done 10 phrases each, if you actually do the statistics on 40, you're more likely to find a difference, but it's a false difference because you've only tested 4 people. These 4 guys here, okay? There's only 4 of them. There's not 40 of them. It would be very different if I got 40 people doing the study. Believe it or not, I've got 4. 4. Sorry, got to stress that one. So many people get it wrong. Most common mistake, you must get a single score per measure for each person before doing any stats. You have 20 users, N is 20. Here we get 4. 4. So in my user test here, I had 26 people, and I've got 26 numbers for the standard, and I've got 26 for the tilting. They actually typed, for the standard condition, they typed 2 practice phrases and then 30 that I counted. So, but I've averaged those before I got here. So for the 30 phrases, I got words per minute for each phrase, and I averaged them to give me the average speed that that person took per phrase in the study. Okay, and I did the same for the tilting condition. Okay, and remember I balanced the study, so half of them did it each way, so that doesn't affect things. Yeah. But I've got one number, this person, I've got one number for each condition for them. I don't have 30 because that would be bad pseudo-replication. Okay, I'd be kidding on there was 30 times the number of people in my study. So the final outcome is a p-value. The probability the difference is down to chance. Normally we seek a p-value of less than or equal to 0.05. Sometimes if it's medicine, lower than that. So if we get a p-value of less than or equal to 0.05, we have a significant difference. We can all clap and go home. We've got a result. Awesome. If it's above that, we don't really know. Okay. It might be you've done a rubbish experiment. It might be your measures are too variable. It might be you've just not got enough users to find the difference you're looking for. That's the most common reason, actually. Or it might be because the two systems are the same. But you don't know. What you've done is you've failed to show that they're different. Okay? That doesn't mean they're the same. It just means you failed to show they're different. And that's standard in statistics. That's just how this test works. It's not a failure review. You just haven't proven it. Okay, Scots law has got this great not proven case. So courts tend to make people guilty or innocent. We've got not proven, which is whoa. We know you did it, but we couldn't prove it, which is a real nasty outcome, actually. It's a horrendous verdict. There are sometimes you might want to use weasel words. If your probability is less than 0.1, you could maybe argue that it's indicative. Okay, actually, what you should do at that point is think, I should do a bigger study. I should do a study with more people, because I might well get a significant result if I did it with more people. If it's over a half, you could maybe argue the data is the same. Okay, but you've not really proven that. So how many users do you need is a big question you get asked in user studies. First answer is if you get a significant result, you're sorted. That's not quite true. If your N is too small, if it's 10 or under, you might just have picked some weirdos. So you've got a population argument there. If it's above that, you've actually got a fair argument that if you got a significant result, then it's meaningful. Okay, if you did it with 20 and you get a significant result, then that's a good answer. That's really good. But you kind of want to plan your user studies before you know your results. So how many people do you plan for? There's a thing called effect size in statistics. Small, medium, and large effects. There's a measure called Cohen's d, which gives you numbers to put to these. It's basically how many standard deviations apart the two systems are. Okay, but in English, small difference is you probably wouldn't notice it. You'd have to do some analysis to spot that there is a difference here. So you might find a significant difference, but it's so small you wouldn't notice it. Okay, if I make you type, if you're typing for an hour and I save you a minute on one system compared to the other, do you care? It's a small difference. And you probably need analysis over lots of users typing the phrases to spot that difference. A medium difference is with a good look, you should be able to see that there's a difference between the data. It looks as if there's a difference. And then you get large effects, which are just glaringly obvious. Okay. The way the statistics work out, if you pick n is 30, you will probably find a medium effect. Okay. So 30 is a good starting point for a user study. So if you're doing a comparative study like this, getting 30 people to do it is a good starting point. That means if there is a medium difference between the system, a medium effect between the systems, you're likely to find it. If there's only a small effect, you probably won't. If there's a large effect, you'll find it with fewer, but if there's only a medium effect and you run it with fewer, you're likely to miss some effects. Okay, so 30 is a good starting point, 20 is okay. How do you calculate all this? You use Excel. So in Excel, there is actually a t-test. Okay. You give it the array 1. You give it array 2. You tell it how many tails you're using, so it's always 2. And you tell it the type, it's paired. Boom. And it says the answer is 0.16. Okay, that's the probability it spits out. Okay, or you use the online tools we've used, or you can actually use, there's a really powerful tool called SPSS, which does lots of statistical testing. You paste your data from the spreadsheet into it, if you're lucky. Then you go to analysis, compare means, paired sample t-test. You check the variables are correct, so they're wrong because I've been doing tests. So you take your two variables, you stick them into variable 1 and variable 2, so that's the variables that are being compared. They come from the heading columns here, and you can change them if you play around in the variable view. Hit OK, and it gives you the means of the two, tells you the n, which is the number of them, okay? And it gives you the standard deviation and other facts. It then does a paired samples test, okay? And for this difference, the mean difference is that, the standard deviation difference is that, lower and upper confidence intervals. And the important things are the t-test result is 2.595, which it's looked up in the tables and converted to a probability, and it says the significance, which is the p-value, for a two-tailed test is 0.16. Okay, so that's the three ways of calculating. And what do you do with it when you've got it? Well, paired sample t, you write a sentence like this, and the green stuff is my study stuff, the grey stuff is stuff that doesn't apply here. So a paired samples t-test was conducted to compare text entry speed in standard and layered conditions. There was a significant difference in the scores. For standard, give the mean and the standard deviation, and layered, mean standard deviation, conditions. Then you give t of 25. SPSS actually spelt that out. The n is 26, we had 26 participants, but you run your t-test, you report what's called the degrees of freedom. Okay, so if you've got two people, you've got 1 degree of freedom because there's one difference you're measuring. Okay, so it's 1 less than the n. Okay, so you actually report 1 under n here, that should be green. And then the result of the t-test, the 2.59, and then p equals that. Therefore, we can, and you would probably add a sentence like, therefore we can conclude that the standard keyboard is faster than the layered keyboard. Sad face. And you might want to include a graph. Okay, graphs are quite easy to do in Excel. Okay. But one of the things that I like to add is a confidence interval. So confidence 0.05. Standard deviation would be the standard dev over the sample of that. Then, oops, bracket, comma, the size is the count of that. Okay. Put that in the wrong place. Oh, ding. Then I drag that right. And this, the 95% confidence interval is, I'll just delete that t-test result here, is a good thing to use as error bars. So I can now take my data, my means, plot them by doing insert graph, column graph. Okay. You should give it a title. So this is speed of text entry. You should then, with the plus thing, add axis titles. Okay. This axis you want to put the scale, so it's words per minute, or WPM. On this axis, there's not much to say actually, so I just say 95% confidence interval error bars. Then you add the error bars. It's a wee bit tricky. You do the plus, then you do error bars, and you hit the wee arrow to go to more options. Sometimes you have to click the bars. Go to custom, specify a value, then you select, here you select the range for the positive error, here you select the range for the negative error, both of which are the 95% confidence. So that shows that if we ran the study 100 times, 95% of the time we're going to get a, we guess we'll get a mean in that range, or we calculate we get a mean in that range. And the thing that matters here is actually the overlap between these two. Okay, because there is quite an overlap in those bars, so it's not a clear-cut difference, but it's not an excessive overlap. So our statistical tests are still showing there is a significant difference. Yeah. And you copy that graph and stick it in your paper as well. Life gets more complicated if you're doing multiple tests. The basic problem is if you do 20 tests with a probability of 0.05, the chance is that you will claim a false result one of those times. Okay, because of that, it's the chances under 5% that it's the same, so we'll conclude it's different. Okay, but it's under 5%, so if you run 20 tests, the chances are against you actually. In one of those cases, you'll tell a falsehood. There are corrections you can do to this, so if you're doing multiple tests, you should actually do Benferroni or SIDAC's slightly less vicious correction. To take your multiple tests, you then, for Benferroni, which is simple, you divide by the number of tests you're doing. So instead of looking for a value under 0.05, you're actually looking for a value under 0.0125. Okay, because just to actually overcompensates, but it compensates for the fact that you're doing multiple tests. Okay, I know there's a better way to go if you're doing multiple tests, but that's a whole different course. Where do you go now? So Social Science Statistics is a great website that gives details of the tests and the calculators. Psychology, I actually really like this little video. It's quite a fun video to watch, and they go over a lot of the details we've covered here. A bit more detail, a bit more background and explanation, and a cool animation. This book is brilliant as well. It introduces you to what you need to know, and it takes you through SPSS to do the standard calculations that we've been talking about here, and it goes on to further more complicated stuff, and it helps you understand things like when you should use a median instead of a mean, what type classifications of data you're using. It's a great little book. Also available as an ebook. That's us. Thank you very much.